quote on the board because the VCR is running.
It's not a VCR.
It's like a VCR, isn't it?
I guess.
Do you know, Hannah, what a VCR is? I'm just kidding, of course you know. However, some people don't. So kids are growing up nowadays, they don't know what a VCR is. You know what a VCR is, Julie?
Kind of.
Okay. Have you ever used one?
Yes.
You have? Okay. Like with a VHS tape.
Yes. I have Spirit on VHS. Spirit the horse movie.
I've got all the Disney
Oh,
movies.
you've got good movies on VHS tape.
Yeah, but I don't have a VCR, so.
So you can't watch them.
Right.
Miss Gibson has one. You can just crash it up and watch it.
Oh yeah, I would do that.
I don't have. Yeah, we have one actually. We have one. We have one machine that we've had a long time that plays VHS tapes and DVDs. Like it does both, either one. And we still have it. Even though it's been a long time since we use it for anything. Okay, that's neither here nor there. Lord, help us to use this period wisely and to learn new things, and I ask you to bless each of these students in the remainder of their day. Amen. We're glad Irma didn't come in and flood Nashville, aren't we? It was kind of not that big a deal. I'd be unstoppable if not for law enforcement. I just wanted that to be on record that I actually said that one time. I'm gonna get fired for that. You realize? Don't post that anywhere because then they will.
The full quote is, "I'd be unstoppable if not for law enforcement and physics," but it's funnier without the physics part.
That's true. It should just stay physics and not law enforcement. I'd be unstoppable if not for physics. That would be bad.
No, it's funny.
That would be bad. That's what's true for all of you watching on social media because Claire posted it when I told her not to. Okay. 12 equals nerd. Here we go. We were talking about this yesterday when we stopped.
We sure were.
You know what? Yesterday the bell rang and I thought we were supposed to be on a regular schedule. But Monday's not regular schedule, it's learning lab day. I just was confused. I think when I get older, I can't think as well. Because Mondays always used to be regular days.
Yeah.
You know, up until this year, every Monday was a regular day. And then we had homecoming week and I kind of lost track of this year and I went back to last year.
It doesn't feel right. Like
I like
Mondays
it.
are supposed to be like dreadful days. You know, just like the regular Monday, you like get back, you're like, there's nothing special
Regular
about
schedule,
today.
nothing special, long periods. Just got to endure it.
Yeah.
No, I think
It's more bearable now.
It's bearable because of Learning Lab?
Yeah.
Oh, come on.
Yeah.
It's a 20-minute thing, the Learning Lab. It can't be that big a deal.
Look forward to.
It makes a difference.
Okay.
Yes.
All of you know what these things are, right? We talked about the units. The T has to be in kelvins. So you know how to get Celsius into kelvins? Do you?
273.
Yeah, add 273. You know what R is? When we use SI units, R is what number?
Oh, I know this.
8.31. And we'll always use SI units, so just remember 8.31. Hannah already said it. Sorry, Claire. And you know what N is? Number of moles. Volume in cubic meters and pressure in pascals, SI units. Okay, so that is what it is. Now somebody came along and said, let's see, which way do I want to go with this first? There, before we do that, I started to take the N and go somewhere with it. But first, let's divide both sides by T. If you divide both sides by T, you get PV over T equals NR, don't you? Right? Have you ever seen PV over T before?
Probably.
It was in chemistry, which Claire remembers, even though probably Julia doesn't. This was we called it the combined gas law. Now you don't have to know these, but I'm just going to remind you that PV equals PV. This was in your textbook though. That's Boyle's law. And then you learn V over T is V over T, that's Charles' law. And P over T equals P over T. And that's Gay-Lussac's law. In chemistry, you learn those as three separate laws. And then we said, look, we can put them all together the P times the V divided by the T, which is what you have right there. And so you can put all those together in the combined gas law, PV over T equals PV over T. And if I were you, I'd remember that too, even though that won't be on your equation sheet, but that can help you solve problems. And the point is, if you look back over here, pressure times volume divided by temperature, that thing, those three variables affect each other. Because when you calculate them like this, you'll always get the same thing, NR. Now, N is the number of moles, so as long as you don't change the actual number of molecules you're dealing with, N stays the same, and R is always 8.31. So that's constant. So that means if this goes up, that has to go down. So you can just look at it. If the T doesn't change, if that goes up, that has to go down. So you'll calculate the same thing. If the pressure increases and the volume doesn't change, then the temperature increases. So you divide them and get the same thing. So you can just think that through. These three all affect each other for a gas. Imagine a gas trapped in a tank. There it is. There's your cylinder with the gas trapped in there. If it's trapped in there, the volume's not changing. So that would just be pressure and temperature go together. They're directly proportional. If you increase the temperature, you start heating that thing, the pressure increases as well. Because when you calculate this, it's got to still equal N times R, which is not changing. N times R doesn't change in that can. Okay? Because N is the amount of gas and R is 8.31. So this is always the same. If that's always the same, then that's what leads us to this PV over T before you heat it or do something to it has to equal PV over T afterwards. So this is, we put little ones there and little twos here. So this is called the combined gas law. You don't have to know what it's called. Just be prepared to use it if you need to. That equation though really does go with this one. The PV over T comes from this one, as you can see. All right, so that's the ideal gas law and the way to think about it using the combined gas law. We're going to be talking about gases for a while, not just chapter 14. So get used to thinking about a container with a gas in it, because that's going to be our example over and over. Now, I was going to do something else with this. Someone started thinking about the N, which is number of moles. And what if we wanted, instead of N, we wanted to use the number of molecules? Or maybe we want to solve this for the number of molecules. Well, that is not hard if you remember that we learned that the number of molecules, the number of moles is the number of molecules divided by Avogadro's number. I think the way I wrote it yesterday was Avogadro's number is equal to the number of particles divided by N. I gave you that yesterday, right there, right? Well, that's the same equation. You just solved it for little n, that's all. So if number of moles is the particles divided by Avogadro's number, which it is, then for a gas that's trapped in a can, the number of molecules is not changing, and Avogadro's number is not changing, so that's not changing. Then we can actually substitute that for n. So I can write PUV equals, instead of little n, I can write capital N over Avogadro's number. Remember, the capital N is the number of particles, the molecules of gas, times R times T. So that's the same thing. Then someone looked at that and said, well, you might change the number of moles. That could be a variable, but Avogadro's number is not variable. R is not variable. So mathematically, I could write that PV equals N times R over NA. Because, and the reason we just switched it over there is the same math. That's the same equation. But the reason we switched the NA to be underneath the R is because those are both constants. That's 8.31. That's 6.02 times 10 to the 23rd. Somebody ought to divide that out, they said, and just come up with a number. And so they did. Somebody divided 8.31 divided by 6.02 E23 and came up with a number and gave it a new name. as a new constant. It's a K. That's the K
What
in
kind of K?
the nict that I mentioned earlier. It's the K.
What kind of K?
It's a lowercase K.
Uh,
but
cursive?
in your textbook it's just a K, and that irritates me. But on the equation sheet you'll get from the AP exam, they made it a little K with a subscript B to identify it as not just another K out of all the Ks we're using. Yes.
The P for pressure. Didn't we always learn pressure was an uppercase P?
We did.
Okay, then make it a big P.
Or does it matter?
Probably. Well, I don't think it matters. However, capital P is better. For one thing, it looks less like the row. The row looks like a little P. So yeah, let's stick with the capital P. Let's do that. All right, and I think it is a capital P on the equation sheet anyway, so I should have been using a big P. All right, so somebody calculated this, R divided by NA, and figured out what it is, and started calling it this, and I think it was Boltzmann who did it. His last name was Boltzmann, because this is called the Boltzmann constant. KB is called the Boltzmann, B-O-L-T-Z-M-A-N, might be two N's, I don't remember, the Boltzmann constant. And it's the number, I don't have it memorized. I have these memorized, so I can still divide them to come up with it, but it will be on your constant page when you take the AP exam. You can always look it up. But what that means is I can now write the ideal gas law as PV equals capital N Boltzmann constant temperature. You could write it that way. And again, KB, Boltzmann constant, is a number you can look up. It's something times 10 to the negative big number, because you can see it's R divided by a really big number. That's 10 to the 23rd, so this comes out to be negative 23rd, I think, but anyway, I don't remember what it is. So these two things in the boxes are two versions of the same law, the ideal gas law. Ideal gas law, that's the one I remember and most people remember, but that's also the ideal gas law. And this one also will be on the equation sheet of your AP exam. If for example, you know these variables and the question is how many molecules do you have, this becomes an easy one to use. Just use this version and solve it for big N. Then you've got the number of molecules. You don't have to do it in 2 steps, which you could have done, but you don't have to anymore. All right. Now what else do I need to tell you about that ideal gas law before we move on? Yeah, your textbook has just a little K, but it will be K sub B on your equation sheet. All right, and it's 1.38 times 10 to the negative 23rd, there it is. But again, that will be given to you if you ever need it. PV is energy. I'm just going to mention that before I erase all this. P times V would be joules. If you took pascals times cubic meters, that would equal joules. Is that really true? And which means nRT is also would equal joules.
So that's just like the unit, right?
Yeah, I'm just talking about units now. Pascal, well, pressure times volume, if you actually multiply P times V and just get a number, that would be energy, because it's joules. If I go pascals times cubic meters, okay, Pascal is pressure, which is F over A. So a Pascal is a Newton per meter squared, F over A Newton over meter squared, times meters cubed would be a Newton meter, which is a joule. See, that works out.
That's crazy.
So the point is, I don't know if you'll ever need to know this, but it is true that P times V is energy, which means if you multiply N times R times T, that's energy as well. That's joules. Joules equal joules. Okay. Okay. Now, The next thing I'm talking to you about, there's a series of graphs I want you to look at, so get your book out and turn to the graph that looks like, I'm sorry. I'm gonna do one more thing first. But you go and get your book out, turn to the graph that looks like, I don't know what page it is, but it's a graph that looks like this. You probably haven't gotten there yet after reading. Because this is in section 3. Whatever page that is, it's chapter 14, section 3. There's some graphs that look like that. Have you found them?
422.
422. Hold that place because we're going to come right back to it. But before we do, I need to make sure you remember this. I'm just going to remind you, but it's been 2 years ago. In chemistry, we learned what STP is. You may need to know that again. Standard, do you remember what? Temperature and pressure. All right, standard temperature is the freezing point of water, 0 degrees Celsius, which is in SI units 273 kelvins. That's standard temperature. It's a little bit cold, but somebody decided that should be standard temperature. We're talking about gases though. Most gases are still gases at that temperature, but haven't condensed into liquids. All right, so that's standard temperature, and then standard pressure is 1 atmosphere, which is about what it is. As you know, we've talked about this. That's about the pressure of the air in the room right now. We talked about this when we studied fluids, and that is 1 and 2 significant digits is 1 times 10 to the 5th pascals. Okay, you might remember that from chapter 11 when we studied fluids. But now you need to know those for the gas laws, since we're studying just gases in this chapter. Standard temperature and pressure. So a problem could just say there's a gas at STP, and from that you know the temperature is this and the pressure is this. Okay? All right. Now for those graphs you're looking at. These are called Maxwell's the Maxwell distribution of molecular speeds. And you need to kind of understand how the graph works, because doggone it, sometimes they put a thing like this on the AP exam. So let's just make sure you understand what's happening here. On the y-axis is probability. What they call it is the percentage of molecules per unit speed. Okay, so as you go up, you're getting, if a curve moves up like that, like it does, as it goes up, the percentage of molecules that are included is increasing, which basically means the probability of the molecules being at a certain speed is increasing. So up here at the top where it curves, that's the highest right there is the highest probability, which means most of the molecules of this gas, most of them are right there in the speed, because the x-axis is the actual speed of the molecules. How many meters per second they're moving, the molecules of the gas. So over here is percentage. It's not temperature, don't think that. It's not kinetic energy, don't think that. This is the percentage. See, down here is a really low percentage are moving. That's slow. That's a low percentage. This is a higher percentage. They're going faster. A really high percentage of those molecules are going this speed right here. That's what it means. And then there are some that are going faster. Now, for one thing you get from this is that all the molecules in a gas are not moving the same speed. You can have an oxygen tank. They're not all moving in there at the same speed. Most of them are moving at that speed right there. But some of those oxygen molecules are going really slow, just a few. Some of them are going a little faster, and so on. Does this make sense? That's what this is about. So that's the kind of blue curve, looks a little bit like this, the blue curve. And then notice it gives you a temperature for the blue curve. That's at 300 kelvins, that's what it says. So this is when you got a gas in a tank, like an oxygen tank, and the temperature of that gas is 300 kelvins. Okay, remember 273 is freezing, so this is above freezing at least. So that's the temperature. They're all at the same temperature, but again, that doesn't mean they're all at the same speed. Most of them, though, are at this speed right here. All right. Then look at the pink curve. The point of this graph, I think, is to look at the two different curves. The pink one kind of does this and goes a whole lot longer. And it's the same two axes as far as what they mean, but notice the pink curve is at 1200 kelvins, much hotter. You take a gas and warm it up, and this curve spreads out and gets lower. Now, what does that mean? That means that if you just think it through, you'll realize what it means. It means, let's say this is the same number of molecules as you had over here. Here you got a certain amount of gas at 300 degrees, and then you warm it up. As you warm it up, it's the same amount of gas. But this curve spreads out. The gas is getting hotter, which means the molecules are moving faster. Now, most of them, that's the highest probability for the gas now, is right here, which is warmer, or not, is faster. This is speed. So most of them are moving faster, but not as many as were here. The range of speeds has increased. Some of them, even at 1200 Kelvin, some of them are still going pretty slow. Some of them are. But just a few. And then there are more going faster, but these never do go this never gets as high a probability as that, but it's definitely, they're going faster. See, these are going faster than those were. And then there's a whole bunch of them even going faster and faster and faster. Because way up here, they're really going fast. So the range of speeds increases as the temperature increases. And if the range increases, that means you don't have as many going at the one speed that most of them are going, but that's not as many. It's not as high a percentage of the molecules as that you had over there. Now, that's just to get you an idea. The whole thing there is to give you an idea of how to think about how gases move when the temperature changes. You know that if you increase the temperature, they move faster. Everybody knows that. But it's not, the number of molecules moving at the fastest is not constant. The hotter it gets, the wider range of different speeds you have. Still, temperature is the average kinetic energy. Do you remember the definition of temperature? And so they're all moving at different speeds, but there's an average. That average is what gives you the temperature. Okay. There's not a problem to work here. There's not a, but you could see graphs like this and just get questions about it. So just make sure you're familiar with what's going on here. And without showing you the graph, you could get questions like, well, what happens when you heat the gas? And here's one thing you know, that of course, the molecules, the average speed is going to increase when you heat it. But there's a wider range of speeds. Okay, and I think maybe that's all I need to really tell you. I just want you to be familiar with that graph if it ever comes up. I think last year's exam, there was no mention of the Maxwell distribution curves, but there has been in the past. 2 or 3 years ago, it was on one of the free response questions.
Wait, are you a reader?
No.
That would stink.
So how do you know? Well, kids told me it was on there. Yeah, sorry. They did. All right, so that's that. Okay. mechanical speed distribution curves for oxygen gas at two different temperatures. I think we covered that. All right. Velocity, root mean square velocity. Some of these, I do hope when you get to the homework that says read the sections, you'll do that, because it will probably make a little more sense to you than just doing nothing but listening to my lecture. We'll explain, go into greater detail explaining. You know that kinetic energy is 1/2 mv squared, all right? All of you know that, right?
Mm-hmm.
What that does is it makes v squared an important thing. V squared is the actual speed of whatever you're talking about, and here we're talking about molecules of a gas. This equation applies to anything, but here we're talking about molecules of a gas. M would be the mass of the molecule, and V is the speed, which we just talked about with the graph. That x-axis was speed, V. But V squared is what's proportional to K. And remember, K is proportional to temperature. The definition of temperature is the average kinetic energy of the molecules. And so, since that's directly proportional, you could say it's directly proportional to V squared. So V squared becomes an important variable, since it's directly proportional to the temperature. But the version of V squared that has been selected to be important is called the root mean square velocity or speed. Mean is average, okay, and that was right there. Average kinetic energy is the definition for temperature, so that would really be average here as well. And there it is. In this term, that means average, mean. The mean is the average. But, and there's the square velocity, which is V squared right there. Square velocity, average square velocity is what that is. But in front of average square velocity, you have the root. Well, that's because, I don't know if I can answer that's because, but I'll tell you what it means. If you had a gas and you knew the speed of every molecule, all right, I'm going to make up stuff. One's going 10 meters per second, one's going 12, one's going 14, and then there's one that's going 16, and then there's one going 18. No, I just made it too hard for me. I want one that I can do in my head. One is going 10, one's going 8, one's going 6, one's going 4. All right, that's good. I'm just making up some numbers. If you want to know this, the first thing you do is you have to square their speeds. All right, so that's V. Well, V squared would be 100, and that would be 64, and that would be 36, and that would be 16. All right, that's the square velocity. Then you would get an average of that. So you'd have to add up those four numbers and divide by 4, which I can't really do that in my head right now.
I got you.
Okay. So add them up and divide by 4. So that would be the average V squared.
45.75.
45.75 is the V average. Is the V squared average. It's the average V squared, to say it that way. The average V squared. Well, the root mean square velocity is the square root of that.
Square root of the average.
Which is going to be about 6 point something, right?
6.76.
Okay, so that's 6.76. So we would say the V RMS, and that's the way it's written, root mean square velocity, for that gas, which is only made of 4 molecules, but that's the way you can do the math, is 6.76 meters per second. All right. Now I'm explaining the term. you're not going to have to do math like this on a test because there is no gas where there are only 4 molecules. Okay, the number of molecules it will be 10 to the 20th or so. It'll be some huge number. So you can't really add them up. You can't square them all and add them up and get an average. But I'm just explaining that is what the term means. If you could square all the V's and then get an average and then take the square root, that's what this number is. So here are the speeds they're going, 10, 8, 6, and 4. Well, the root mean square speed is almost 7. Yes?
Wait, I'm kind of lost. So you like added the v squared together. Like
right.
All the v squared together and then you divided by
4.
Oh,
just to get an average.
Oh, okay.
Yeah, add them up, divide by 4 to get an average of the 4 numbers. Again, you will not be asked to do that math, but if you understand the math we just went through, you understand the term root mean square velocity. I'm gonna give you an equation you can use to find the root mean square velocity, but this is what the term means. It's not the average speed. See, it's the average of the speed squares, and then the square root of that. So if you added up the V's and took an average, it would not be 6.75. It would be 10, 8, it would be 7, I guess. 4, I don't know. Yeah, so it's very close to the same thing. The average of that would be 7, am I right? Just looking at it. The root mean square velocity though is less than 7. So the reason, again, you might say, well, why don't you just take the average speed? Well, the reason is because of this relationship right here. Temperature is not proportional to K, to V, it's proportional to V squared. And so that's why when we want an average kinetic energy, we've got to deal with the root mean square velocity, not just the velocity, not just an average of velocities. You get an average K, remember they're not all moving the same speed. According to those graphs you just looked at, they're all moving different speeds. But to get an average K, we have to take an average of all the V squares. That's what you have to do. Is the bell about to ring?
I think it is. Yeah.
I think we're on learning lab day because it's Tuesday. It's at 49, so we're okay. I haven't shown you yet how to calculate this, so let me do that. This is just explaining what it means. Now let me show you the equation. There's an equation you have that is usable if you have a large quantity of gas. And it's this. VRMS is I don't think there's any point in me trying to explain how we came up with it. I'm not sure I could anyway. So I won't try. It is, I think the number is 3 RT over M. I should check to make sure before you write that down. I don't know if it's in my book or not. VRMS is 3 RT over M. Yeah, that's one version. There's another one. But first, let's just talk about this one in a little bit of time we have. The 3 is obvious. That's just a constant. The R is 8.31, as it was before. That's the ideal gas constant. T is temperature in kelvins. So see, you don't have to know the number of molecules. That would be impossible, probably. You just need to know the temperature of the gas. The capital M, though, is what we talked about yesterday. It's the molar mass. The capital M is the mass of a mole, or molar mass. You can get the molar mass from the periodic table. Remember that? If it's oxygen, you would have to remember that oxygen is O2. And then you would take the number on the periodic table, which is 16 and times 2, and so its molar mass is 32. However, it's 32 grams for 1 mole, and gram is not the SI unit for mass. What's the SI unit for mass? Kilogram. So we've got to change 32 grams to kilograms when you plug into this. So the M here would be 0.032. I'm just reminding you that here you're gonna have some converting to do. Cause we get molar mass from the periodic table, but that number's in grams, and you gotta change it to kilograms. Everything else, the temperature has to be kelvins, you know what it is. If you just plug in numbers here and calculate it, you'll get the VRMS guess. Now, we'll come back to this tomorrow. Your homework tonight, I don't think has any of this in it. And so we'll come back to this tomorrow and come up with the other, there's another equation for VRMS as well. And probably finish up the lecture part of this chapter tomorrow.
Oh, sweet. So then we can just like.
And then we can just go over homework Thursday and Friday. And Monday, I guess, because the test is scheduled for Tuesday. Assignment B due tomorrow.